Okay, up to this point, our primary use of regression has been to have a single predictor. So we had mother's weight at one point, and then we had race. Now that got split into two variables, but it was still a single construct that we were dealing with. But an advantage of regression is the idea that you can get multiple predictors in your analysis. Okay, and so what we're going to do is we're going to illustrate the concepts by adding two more variables to our model. The first is going to be smoking history, and then the second is going to be mother's age. Okay, and if you were to analyze this data for your own studies, I'd want you to be a little more specific or deliberate about why you'd pick particular variables and that sort of thing. But my goals here are primarily just to teach you the ideas and how to do things like interpretation. And so just bear that in mind. Okay, so the first thing we're going to do is we're going to build a model like we've done before. And when you add predictors, you're basically going to add it over here on the right-hand side of the equation. Okay, so remember, regression, as we're covering it in this class, has only a single outcome variable. So we're going to keep that as birth weight. And then we're going to add in the smoking status, okay, whether the mother smoked during pregnancy, age of mom, and mother's last weight. Okay, as you can see, the smoking status variable is a dummy variable, with our reference category being no and coded as 0, and our comparison condition being yes, that the mother did smoke. Age of mother, which would be a continuous value, and then mother's last weight, which we've dealt with before. Okay, so if we go ahead and drop these variables into the regress command in Stata, you get the following output. Okay, notice that this top part is the exact same, not the numbers, but the structure. The top part is exactly the same as it was with a single predictor. Down here will be the coefficient you get. Okay, and what we're going to get is we're going to get our regression slopes and our constant, our intercept, just like we did before. And then you get your standard error, your t-value, and so on as part of the output. Okay, so looking at the top part first, the sums of squares are the same as they were in bivariate regression. So you have the model sums of squares and the residual sums of squares, where the model sums of squares tells us the amount of variability in birth weight that's accounted for by, in this case, the predictors in the model. Okay. Then the residual sum of squares is the amount of variability in birth weight that's left over after we deal with those three predictors. The f-test is the same as it was in bivariate regression. Then basically the null hypothesis here is that these predictors as a set, so smoking, age, and mother's last weight, that as a group, they're not related to the outcome. Okay, and so you can kind of think of that as that the model accounts for no significant variance. Okay, R squared is still the proportion of proportion of variance in the outcome accounted for by the predictors. So it's all three of them here. And the root mean square error is the same as it was before. So it's just the average error in prediction. But now that, remember, the predicted score in this case is going to be in this case it's going to be based on all three variables. So we're going to create a predicted birth weight based on whether that baby's mother smoked, how old that baby's mother was, and what the mother weighed at the last menstrual period. Okay? So let's think about what the interpretations are. Okay? Okay, so first let's think about our intercept. Okay? So as I've told you, the intercept is the expected value of y, or the outcome, when all variables are 0. Okay, so we can think about that as this is the constant, this 2363 right here. That is the expected birth weight for babies whose mothers did not smoke, because there's 0 on that. Okay, who also have 0 on age and 0 on weight. Okay, and so as I'm saying that, I think you should be able to, or you should start to think, wait, that doesn't make any sense. How can age be a 0 value, right? And how can weight be a 0 value? How can you have no age and no weight? Okay, so that doesn't make any sense. and here's the rub, here's the critical thing. Remember that even though age and birth weight, or age and last weight, don't actually ever take on a 0 in the data set or even in real life, that is still the interpretation of the intercept. The intercept doesn't know whether 0 values on your predictors are sensible or not. Okay? So as you're interpreting your parameters, you got to bear that in mind. And this is going to be especially important as we start to build in interactions into our model, because what 0 means in our predictors is going to matter for our interpretation. Okay, so just like we did before to deal with that, we mean-centered. Okay, and that helps us have more meaningful interpretations or more meaningful values for things like the intercept and that sort of thing. So in the first set of lectures, we used regular mean centering. Now we're going to use z-scores. And here's our formula for a z-score. So you should have seen that in your introductory statistics. The thing I want you to pay attention to right at this moment is that numerator. Notice that is just mean centering, right? You take each observation, you subtract from it the mean. So z-scores are a type of mean centering. It's just now you divide by the standard deviation to put that centered value in standard deviation units. Excuse me. So we're going to create 2 new variables. Okay, I'm going to call them, I'm just going to put a z in front of them, and I'm going to z-score both age and mother's last weight. Okay, so I've gone ahead and created those values in Stata, or those new variables, excuse me, and I'll show you the mechanics of that in class. Okay, so then we have our these z values right here. So what I've got here on this screen is up here on the top we've got the unstandardized predictors, the regression model from that, and down here with the standardized predictors. Okay, so we have the uncentered values, the z-scored values. Okay, so what I want you to pay attention to here is why might the intercepts and the slopes be different for age and weight, and also the intercept, but why might smoke stay the same? So why do these change? These 3 are different, and then why is this one the same? So I want you to pause for a second, and I want you to think through that. Okay, so the reason that these things are different is, let's start with the constant, right? That's the expected value of birth weight when everything is 0. Well, when we center this, 0 now is not 0 age, like no age or no weight. It is the average age and the average weight. So this value down here becomes the expected birth weight for babies whose mothers didn't smoke, because it's 0 on that. We have a 0 value on the z-score for age, which shows at the mean age and at the mean weight. Okay. All right, so what might this thing mean, right? So age here is that a 1 unit increase in age is associated with a 7.04 difference in birth weight. Okay, so let's think about our units. In age, this was just year. So this, for every year increase in age, you expected a 7-gram increase or difference in birth weight. Okay, when we z-score things, if you remember from your introductory statistics, a 1 unit value, so going from 0 to 1 on a z-score, is a 1 standard deviation change. Okay, so this now represents a 1 standard deviation change in age is associated with a 37-gram difference in birth weight. The same thing here with mother's weight, right? This was in pounds, this is now in standard deviation units. So this is a 1 standard deviation unit difference in mother's last weight. Okay? Now, we didn't change smoke at all, right? It's in the same units as it was before. And so it just remains the difference between mothers who smoked and mothers who didn't. Okay, so let's walk through this one more time. Okay? So if we interpret each of these coefficients, okay, for this first one, the intercept is equal to expected birth weight for smoke equals 0, Z age equals 0, and Z weight equals 0, right? So for expected birth weight for babies whose moms didn't smoke, who are the average age and the average last weight. Smoke is the difference in expected birth weight between moms that smoke or smoked versus no smoked. Z age, it's a 1 unit difference, but remember that 1 unit difference is a standard deviation. So 1 standard deviation difference is associated with a 122.7 gram difference in birth weight. Same thing here. 1 unit difference, with that being a standard deviation difference, is a... Oops, I did this backwards. So this should have been, the 122.7 is here. And this one is 37.24. Okay? All right. Okay, there is one key thing that we need to pay attention to, though, is all those interpretations we had on the last slide are correct. It's just now we have one other wrinkle because we've introduced multiple predictors into this equation. And that is that these slopes are now called partial slopes. And what a partial slope says is that a 1 unit difference is associated with a b difference in the outcome. So that's what we said on the last slide. But now we add this piece out here, holding constant other variables in the model. Now I want to draw your attention to this part. Like this is critical. Okay? Whenever you're interpreting things in this class that have multiple predictors, I want you to write that out. Okay? I want you to state that you're holding constant these other things, because partial slopes are different from regular slopes. And what you put in the model is going to affect what those slope values are. And so you need to make sure you understand what you're holding constant and what you're not, what you're controlling for. Okay? Holding constant is another term for statistical control in this instance. So if we think about what does holding constant mean? Okay, so what I've got here are predicted values. Okay, so each dot is a predicted value. The red dots are for mothers who smoked. The blue hollow dots are for mothers who didn't smoke. On the x-axis down here, we've got the age, mother's age, but remember this is a standardized value, so this is the average right here. And this linear prediction is the predicted birth weight over here. Okay? All right. So, look at this difference here. Yeah, you can pick any two. Okay? Note that this difference stays constant no matter where you are at on age. So no matter where you're at on this variable on age, so wherever the mother was, down here, that difference stays the same. That's what holding constant means, is that we're going to hold constant any of these values, which is essentially saying it won't matter which of the values we pick, we're going to get the same difference between mothers who smoked and mothers who didn't in terms of expected birth weight. Okay? You can also think of these lines as describing the relationship between age and birth weight, right? So how much does it increase? And so if you look at either of the lines, it doesn't matter which, but you're looking at these increases, right? Any of those increases, that increase from one part to the next, that step up from here to here, and then from here to here, and so on, those are going to be the same regardless of whether the mom smoked or not. That's what it means to hold constant. Okay? And that can be a good thing. That can be problematic. It kind of depends on the research question that you have, whether holding constant makes sense or not. And I'm going to show you a way in regression to be able to essentially relax that assumption sum and allow variables to have relationships that are with the outcome that are a function of another variable. And those are called interactions. Okay, so to wrap this section up, I want you to think for a minute. And after you read these questions, pause, and I want you to think about it for a second. I want you to think, what are the best kind of predictors in a regression model? What I mean is, suppose you want to predict the baby's birth weight and you could only use 2 predictors. What characteristics would you want those 2 variables to have? So go ahead and pause the video and think about that for a minute. Okay, now that you've thought about this, what I'm going after here, and you may have come up with several things, but one that I want to highlight or make you aware of is what we want 2 variables. Remember, this question here says you can only use 2 predictor variables. And so what we want 2 predictors that have a strong correlation. So they each are strong correlation with the outcome. But so that both x1 and x2 are strongly related, but the x1 and x2 are uncorrelated. So essentially, when they're uncorrelated, that means they're independent. That whatever you're learning about y from x1 is independent from what you're learning from x2. Because you can imagine a situation where x1 and x2 are perfectly correlated. If you know the relationship between x1 and y, if x2 is perfectly correlated with x1, then you know what the relationship is between x2 and y. Okay, so they're fully redundant in that case. And that's no good. That's not helpful. That's no good both from a mathematical perspective. If you have perfectly correlated variables, that's a problem. But you can think scientifically, that's just not very interesting. And so what we want are independent predictors. So I just want to show you this figure. This is from the textbook, and what we've got here is on the y-axis or x-axis we have the correlation between 2 predictors. Okay. On the y-axis we have r squared, so that's the proportion of variability that's explained in y. Okay. What each of these lines represent is how correlated the predictor, so in this case x1 and x2, how correlated x1 is with y and how correlated x2 is with y. And when I made this graph, I made that the same value. So if x1 had a correlation of 0.2, x2 had a correlation of 0.2 with y. Okay, so we have 3 values of that. Okay, so what you see is that when the x1 and x2 are uncorrelated, so they have a value close to 0, that as the correlation between y and the predictors goes up, so as we go, right, it's smallest here, medium here, and biggest here, that the difference between these lines is the biggest. Look, it's much bigger up there. Okay? And that's because they're fully independent and you're getting the most bang for your buck in terms of your predictors. But notice as you move to the right-hand side of this graph, and so as the correlation between the predictors is getting stronger, that these graphs are coming closer together. So what's happening as you go this direction, right, as you go across here, you're increasing redundancy in the predictors. Okay, you get more redundancy. And when you get more redundancy, you're explaining less of the total variability because that shared variability doesn't help.